recently we did a video on the most mysterious and beautiful identity in mathematics. E to the pi I is equal to -1. Comes up 3 times in The Simpsons, which of course makes it even more important. Now, afterwards, a few people challenged me to come up with an explanation that even Homer can understand. And I've actually been agonizing over this ever since. And today I want to do just that. I want to explain e to the pi I is equal to -1 to someone like Homer. Okay, someone like Homer who can only do addition, subtraction, multiplication, division. So we have to remind him or tell him 2 things. The first one is that I is this strange complex number, square root of -1. I squared is 1. The second thing is just kind of a reminder. If you've got a semicircle of radius 1, then the length of the semicircle is pi. Okay? So keep those 2 things in mind. We have to use them later on. So the first thing I have to explain to Homer is, what is E? E. So to do that, I give him $1. And I tell him, go to the bank. Now I've arranged with the manager here to give him 100% interest over a year. Okay? So what happens to this $1 when Homer puts it in? Well, after 1 year, he has 1 plus 1 is $2. Okay? So he's got $2. Now, this is actually not the best you can do with 100% interest. You can do better if you find a better bank. And we found a better bank, the Second Bank of Springfield. The Second Bank of Springfield, they calculate and credit interest twice a year. So after 6 months, what happens? You get 50% on what you've got there, so it's 50 cents, it's got $1.5. Now, another 6 months path. Half of that is 0.75, so you have to add that to 1.5, and it gives you 2.25. That's what you've got at the end of the year if you calculate and credit twice. Now, at the Third Bank of Springfield, they do it 3 times. So what do you get? After 4 months, you get that. After 8 months, you get that. And at the end of the year, you've got that, even more. Okay, and it's actually quite easy to figure out the general formula for this. Well, maybe Homer can't do it, but I can do it. So it's this one here. And you can probably do it too if you're watching this video. So it's 1 plus 1 divided by n to the power of n. So if you credit n times throughout the year, that's how much money you have at the end of the year. Let's just check it for the simplest cases 2 and 2.25. So for n equal to 1, we've got 1 plus 1 is 2, is 2. Okay, 1 plus 1/2 is 1.5, squared is 2.25. Okay, works, okay? Works in general. Now, this is really good news, but maybe what you think now, and Homer definitely thinks this is, well, I divide more and more, and I get more and more money, so if I just divide enough, maybe I get $1 trillion at the end of the year. Sadly, that doesn't work, okay? So, for example, if you divide into 125 parts, you get that much money at the end of the year, or have that much money at the end of the year. Now, if you crank up the n, what happens is, well, that number goes up, but it goes up very slowly and actually settles down to a number. So if we push the whole thing to infinity, we take the limit of this, we get this number here, $2.718. And that's the absolute maximum. That's continuously compounding interest. That's what it is. So you can't do any better than this. That's E. And that's also where E kind of comes up for the first time historically. Exactly this sort of consideration, okay? Cool. So now we've got E. We're ready to move on. E to the pi I. Well, not so fast. Let's just go to e to the pi first, which is actually almost as mysterious as e to the pi I. Why is that? Well, it's got a special name. It's called Gelfond's constant. And eventually I'll definitely make a video about this one. But just for today, just ponder it a little bit. What does this actually say? Well, it says weird number to the power of another weird number. And you're supposed to calculate this. How do you calculate something like this? If I give it to you on a piece of paper and you don't have a calculator. That's strange. I think nobody will be able to do this. Well, it would be doable if pi was equal to 3, because then we know we just have to kind of multiply, maybe chopped off bits here 3 times and together, and we get rough approximation to what we're looking for. But no, we have this one here. So we really want to calculate this. We want to really know, for some strange reason, how much money Homer has after pi years if we're compounding interest continuously? That's what we want to know. We can't go to sleep tonight if we don't know. Okay, now the trick here is we have got this bit here, which gets us closer to E the more we crank up this n. Okay, and so if I put that one up here and put a large number in here, we get the right thing, or approximately the right thing, or as close to the right thing as we want. All right, now that looks still pretty awful, okay? And, well, let's muck around a little bit with it. So the first thing we do is we multiply by pi here and there. And so if we do this on the top and the bottom, obviously nothing changes. It actually looks a bit uglier than before. But what's nice here is that these two bits are the same. And, you know, what you have to do now to get this is just crank up the bit in the box, right? So n equals 1, we have this, n equals 2, we have that, and then that. And that's still pretty awful. Except, what's really important here, and that's a really, really nice trick, is what's really essential here is that we're going up. It doesn't matter how we're going up, as long as we're going up towards infinity, we can go up by nice numbers. 1, 2, 3. That will also get us there. And that's actually what we do. And this here is exactly what we're looking for, right? So it's like really awful to the power of awful. But now we've just got addition, division, multiplication. That's all we have to do, right? Just a lot. But that's basically all we have to do, right? So, you know, getting there. And of course, the pi here stands for really any number whatsoever. So what we've done now is actually we've figured out how to calculate the exponential function, which basically nothing, right? Which just this. That's what we've just figured out. That's pretty good effort, right? So, well, let's just graph this and a couple of those guys and see what happens, right? So I've graphed the exponential function, and I graphed the first one of these guys, well, the second one really, where we take the m is equal to 2. So we've got this guy here. Not a terribly good fit, but if you crank up the m now, you can really see how good this gets. And actually, when you press, the button on the calculator, that's what your calculator does at some level, right? It just adds and multiplies and divides and does these sorts of things. That's all you can do. Anything complicated in mathematics, when you do it numerically, has to be reduced to just basic arithmetic. Otherwise, it doesn't work. Okay, here we go. Almost there now. Just chuck in your pi I, that's what we're interested in, and go for it. And actually, we could go for it at this stage. It's actually not very hard to multiply things like this. Well, this is basically a complex number in here. So we've got a nice number plus a nice number times I. This weird. It's actually not very hard to multiply a couple of those things together. I could teach you in a second. Actually, I'm going to teach you in a second and just do it. Let's just do it on Mathematica and see what Mathematica spits out. So for m equals to 1, we get this number here. It's also a complex number. Doesn't matter what you put up there. Doesn't matter what m is. The result is always going to be a complex number. Right? So let's just crank it up now. Crank it up, crank it up, crank it up. All the way to, what did I do, 100. Okay, and you can see that this first bit here gets closer and closer to -1. And the second bit here, that nice number in front of the I, goes to 0. So basically the ugly part goes away, and we're left with the -1 if you kind of go to infinity. And we could stop here, but actually I've got this really, really, really nice way of multiplying complex numbers, which you can apply to this, multiplying complex numbers with triangles. I wanted to show you. Okay, so here we go. Now, complex numbers you can draw. Like real numbers you can draw on the number line. Complex numbers you can draw in the xy plane. Actually, Homer stands right on top of the xy plane, so we might as well use it, and he can really relate to it at this point in time. So here we've got the real number line. So there's 0, there's 1, there's 2, and so on. And, well, we've extended this real line by the complex plane. It's just this whole thing. So every complex number corresponds to a point in here. So, for example, 1.5 plus I is just the point where you go 1.5 over here along the x-axis and then 1 up, direction of the y-axis, okay? And then this guy here, for example, 1 plus 2i, well, 1 over here, and then 2 units up. Okay, now, let's multiply those two things together. Right, so what do we do? Well, we do 1 times 1.5 is 1.5, then 1 times I is I. 2i times 1.5 is 3i. And then the last one, that's where we have to kind of remember that I squared is equal to -1. So this is -1 times 2 is -2. Now we just combine things together in the obvious way. So there, and that's the product. And of course that corresponds to a point, that guy up there. Well, how do you get from here to there? Not obvious, right? We couldn't do this, but you can actually see it at a glance. You can see at a glance that these two guys get you up there. How? With triangles. Okay, so to every point, to every complex number, we associate a triangle. And the corners are 0, 1, and that point here, okay? So that's the first triangle. Let's just save it. Second triangle, 0, 1, point. That is guy. Now we align them, like that. Stretch this one, the red one, so that these two sides are the same. And there's your product. Brilliant, isn't it? So you just kind of align and stretch these triangles and you know what happens. And actually, if you know the triangles, it's pretty easy to predict where the product's going to be. Let's do another example. Let's do this one here squared. So what you need for squared is the same triangle twice. Okay, stretch it. That's a square. Now, cubing, and we're going to have higher power, so we need to see what happens here. So we just make another triangle, stretch it. That's the cube of this number here. All right, now higher powers. That's the complex plane. For the higher powers, this circle here, the unit circle, the circle of radius 1 around 0, plays a very, very special role. Why is that? Well, here's a complex number on that unit circle. The triangle that corresponds to it has two equal sides, there and there. So when you align two such triangles, what happens? Well, you don't have to stretch, right? You don't have to stretch. And let's just see what happens when I kind of raise this to the power of 8. Second power, third power, fourth, fifth, sixth, seventh, 8. That's the 8th power of that guy here. So this power, well, spiral or whatever you call it, it's just kind of wrapping around the unit circle. So it doesn't matter how high a power you choose, it's just going to end up somewhere here on that circle. And what happens when you kind of move that guy here off the unit circle? Let's just move it inside. So we move it inside, and what do we get? Well, we get this nice spiral here, kind of spiraling inside, okay? And actually, if you go higher and higher, that goes closer and closer to 0. If we move this guy outside, well, it's always going to be a spiral, but the spiral kind of spirals outside. Main lesson to take away from this is that the closer you start at the unit circle, the closer the spiral, this power spiral, will wrap around the unit circle, okay? So now let's go for the real thing, the one that we're really interested in, okay? This guy here, so there's the complex number here in the middle. What is that? Well, it's 1 over here, and then we have to go up pi divided by m, so that's kind of going up there. So let's just go for m is equal to 3, okay? Let's just draw this. So there we go, 1 over here, pi over 3 up there, and then we have to do cubes, right? So 3 times, same triangle, scaling, and so on, what we've just done, and it gets us over there. Okay? Right. Now, what's going to happen when I make this m bigger? Okay, well, the one stays the same. I make the m bigger, that means that this number here gets smaller, right? Gets smaller. That means that it's going to wander down here. It's going to get closer and closer to this point. And actually, I can make it as close to this point as I want, right? As close to 1 as I want. By making m bigger and bigger. It's just going to wander down here, down here, down here, down here. Means the spiral is going to wrap close to the unit circle. Well, let's just do it, okay? So, crank up to 4 triangles now. Crank up to 5 triangles now. It's wrapping closer, right? 5 to 6. Now, let's just let it go and see how that guy here gets closer and closer to -1. It's real magic happening, about to happen. So ready to go for the magic? Okay, there we go. Cranking it up all the way. Well, not all the way. Up to 100. But you can see it's really getting closer and closer to -1. So it's pretty obvious why, right? I mean, the bit that's obvious so far is that because that guy here wanders down and down, it gets closer and closer to the unit circle, we should get a closer and closer wrap around the unit circle. But what's not clear at the moment, maybe, is why we don't wrap further or closer. Why do we just go halfways around? And for that, you have to remember what I said at the very beginning, this reminder about the length of this semicircle. What's the length of the semicircle again? It's pi, okay, it's pi. And, well, what is this? This is the mth part of pi, okay? So basically we're starting out to the mth part of pi here, and then we're doing this m times, so pi divided by m times m is pi, so we're going to eventually wrap around halfway, smack on, right? And we're going to get e to the pi I is equal to -1. And I think this is the way to explain it. And hopefully, well, I don't know about Homer, but hopefully you, who are all masters of plus, minus, multiply, and so on, got something out of it.
It's mind-blowing. I learnt this